Hello everyone, my name is Ludwig Sidemark and I'm a PhD student at Lancaster University. I will present my project named Weighted Pointer Error-Aware Gaze-By Interaction through Fallback Modalities. This project was a result of a research internship at Reality Labs Research last summer, and I'd like to thank my collaborators Mark Parent, Chi-Hao Wu, Johannes Chan, Michael Glueck, Daniel Vigdor, Tove Grossman, and Marcelo Giordano for their support and a great internship experience. When dealing with multimodal input streams, the quality of each available signal can vary over time due to a variety of factors. For example, eye tracking can be very attractive for interaction as we naturally look at objects that we're interested in. However, eye tracking can become noisy and for some completely unusable. To address these limitations, several projects have proposed the inclusion of a secondary modality to refine inaccurate gaze directions. However, these techniques require users to manually detect, switch modality, and then refine errors that are present. Alternatively, gaze-based error-aware systems have also proposed adjusting the interaction based on eye tracking error by, for example, adjusting one's gaze position to account for accuracy errors or to increase the size of interface widgets to overcome poor signal quality. Although all these approaches can be useful, they usually only focus on one error type, mostly accuracy, and all assume that there will be a stable output of gaze samples that can be used to 1. Accurately adjust the signal or interface, or 2. Be used in combination with a second modality to refine or disambiguate one's pointing position. However, stable eye tracking output is not guaranteed for all users or contexts. This can be very easily noticed when you read eye tracking papers where participant data was discarded due to calibration or tracking. In user studies, it is of course fine to discard participants from analysis, but this is not ideal for interaction with commercial devices. Thus, this research proposes the use of fallback modalities to make gaze-based systems more robust and accessible to users. So we want to base the design of our interaction techniques on 4 goals. First, the techniques should provide stable interaction, irrespective of the eye tracking error level, including when the eye tracker is unusable. Second, the technique should decide the modality for the user rather than manually switching between modalities, as is common in prior techniques. Thirdly, determining whether a gaze signal is too inaccurate or noisy for interaction should depend on current interaction needs. As such, the techniques should accommodate an application's required level of interaction granularity. And finally, as the movements performed by the user may be different when using gaze or the fallback modality, the user should be able to understand whether they are currently relying on gaze or the fallback modality for interaction. To achieve this, weighted pointer consists of 3 steps. First, an error detection model to derive eye tracking accuracy, precision, and data loss. Second, a modality weighting model that utilizes the data from the error detection model to decide on the weightings between gaze and fallback modality. And finally, the interaction technique that uses the weightings from the modality weighting and the modality's pointing positions to calculate and display the current pointing position. And I'll go through each step now. Our error detection is similar to other error-aware gaze work. So to measure precision and accuracy, the user performs a typical eye tracking calibration procedure where they are asked to fixate on a set of points scattered across the HMD. The tracking area is then divided into a grid where the accuracy and precision error can be retrieved during use from the closest calibration point on the nearest neighbor approach. And to measure data loss, we simply track the ratio of missing data versus all data points. And we also use some simple velocity and acceleration-based filtering to remove potential outliers and artifacts related to data loss. So the second steps involve deciding on whether the eye tracking signal is good enough for interaction or if it needs support from other modalities. And we use a continuous sigmoid function that outputs a number between 0 and 1 to decide the relative weighting between gaze and fallback modality. And as the input for this function, we use the sum of accuracy and precision error retrieves from the previous error detection model. And here we use a continuous function so that users can rely on gaze as much as possible, and also allowing lazier pointing with the fallback modality when using a combination of gaze and fallback. And this function, the sigmoid function, is defined by 2 parameters that takes into account the current interaction needs. So we have the acceptable eye tracking error that we deem to not affect interaction, which is the green line, and we have the maximum error where the eye tracking is so bad that we deem it unusable, which is the red line. And then we have the curve in between those. And so based on the errors that we get from the error detection model, we then end up somewhere on this curve, which decides the relative weightings of gaze and the fallback modality based on this curve. And then finally, to account for data loss, we then normalize the retrieved weightings based on the ratio of valid gaze samples. So finally, when we have the weightings available, we should then use them for interaction. And we came up with a set of techniques that we call the weighted pointers, which are generic raycasting techniques designed for pointing-based interaction while using head-mounted displays within AR and VR. So using this technique, the gaze and fallback directions are added to a shared distribution on a rolling window, and the pointing position is then calculated by the weighted mean of this distribution. So a user's pointer position will then be fully dictated by gaze if the gaze signal is deemed accurate and stable enough, as we can see in A, or as the gaze signal deteriorates, as we see in B and C, it will increasingly rely on the fallback modality until the pointer position is completely dictated on the fallback modality, in this case the head pointer. And to visualize whether the interaction relies on gaze or fallback, we use cursor transparency. So the cursor is invisible while relying on gaze, and gaze on targets are highlighted for feedback. However, as the fallback takes over interaction, a cursor is displayed and the cursor's transparency is decided by the current weightings. So as the choice of fallback modality can have significant impact on the technique's behavior and one's user experience, we have developed 4 technique variations with different modalities as fallback. So the hands-free weighted pointer uses head pointing as a fallback modality to allow fully hands-free and accurate interaction. As the head is used as a natural part of our gaze movement, the transition from gaze to head pointing should be simple for users to understand, as the pointer is guaranteed to always be within the field of view. The controller-gazed weighted pointer uses controller pointing as the fallback modality. And we quickly realized that switching between pointing origins, i.e. the head and controller, could be easily confusing. So the pointing origins is always set to gaze, to the gaze origin, to avoid confusion during modality transitions. Therefore, the techniques only requires a 3-degree of freedom controller for interaction. And here we assume that stable tracking of the gaze origin can be achieved via head tracking. So the relative weighted technique uses relative hand movements to minimize the required head movement and allow small adjustments to the pointed direction from a lazy resting position. So here we use a standard VR controller, and these movements are made relative to a calibrated neutral controller direction, and the offset between them is then applied to the gaze direction as a fallback modality. The tremolo technique uses, again, relative controller movements similar to the relative technique. However, the controller adjustments are relative to the head direction as the fallback modality. This allows for a combination of head and controller movements to be used to adjust the pointed direction. Large adjustments can be performed with less straining movements because the refinements is distributed to both modalities. Also, in contrast to the relative weighted pointer technique, the fallback modality is not based on the gaze direction and should thus be more stable during high levels of precision and data loss. So we conducted a VR user study to gather insights into our proposed techniques, performance, and to gather user feedback at different levels of eye tracking error. So in this study, the weighted pointers were combined with a button click for target selection, and we had participants perform selections at different distances and directions, while precision error, accuracy error, or both were injected to investigate different severities of eye tracking error. And we also compared our techniques against the eye plus head and eye plus device pinpointing techniques, wherein the user first point with gaze and then switch to either head or controller via a button press and hold down, which displays a cursor at the gaze position, which they can then refine, and then selection is finally performed via a button release. So to summarize the results of our study, which I'll only do here, if you want to read the full results, please refer to the full paper. Our approach of using error-aware fallback modalities led to higher performance and user preference, as it requires less interaction steps and users can rely more on gaze in comparison to our baselines. We also found that the choice of fallback has a significant impact on the performance and user experience. In our case, the head was more performant and stable than the controller, probably because users perform more head movements already as part of their natural gaze movements. And we also find that the relative motion can be used to lower the required movements to perform selection. However, we also found limitations in the design and implementations of this techniques. And then finally, we also found that the visual feedback alone is not enough depending on the choice of fallback modality, and that transparency is not useful to highlight the current mode of interaction. Finally, I'd like to get into some limitations and future avenues of research. First, a current weakness of our implementation, similar to other existing error-aware techniques, is that they are dependent on a user calibration procedure to generate the data needed to model eye tracking errors. Ideally, the eye tracking detection model should seamlessly detect and update itself without the user having to perform repeated calibrations. Furthermore, adapting interaction to the current signal noise is not limited to gaze-based interactions and eye tracking errors, but may also be useful for other senses that have tracking issues, or even participant-specific factors such as hand tremors. Also, the concept of switching modalities could be further expanded to include switching based on other factors such as social acceptance or available range of motion. For example, one can imagine a hand-based interaction system that switched to gaze as a fallback in crowded environments where one's range of motion may be limited. And this opens many research avenues to investigate ways of switching modalities based to ensure a comfortable and efficient interaction no matter the current context. And then finally, exploring fallbacks for other modalities than gaze, interactions other than ray-based pointing, and feedbacks other than visual cursors are some things I think could be very interesting to look into for the future. So to wrap up, adapting the interaction to the signal layer can increase the performance and user experience when noisy data is present. However, the choice of modalities to use for interaction has a significant impact on performance and user experience and has to be carefully considered. And that is all for my talk. Thank you for listening.